So without further delay, let me turn over the reins to Tyler, who is our presenter today. And with that, welcome and thank you, Tyler.
Thanks a lot, Karen. Hopefully you can hear me okay?
Yes, we can hear you fine. Thank you.
Okay, just making sure. Thanks, everybody, for calling in today and listening to our presentation. This is the first in a three-part series that we're titling Get Fiber Smart. The intention of this is to give folks in the industry, particularly focusing on enterprise environments and applications, an opportunity to strengthen their knowledge base on the issues that are facing technicians in the enterprise today, specifically as it pertains to fiber optics. This first one focuses on best practices for connectivity. The following one, part two, will focus on the fundamentals for best practices for testing Tier 1. And the third one will be focusing on best practices for testing Tier 2 fiber links in the enterprise. And those will be coming up in the following months, in the months of May, June, and July. And with that, I'll go into our agenda. Today we're going to start off with a brief overview on fiber optic connectors and then highlight particularly contamination and some of its impacts on network performance. And then from there, our real focus will be on the next section, best practices and standards. Particularly, we'll be highlighting standards as it pertains to the IBYC, and then how that's transitioned now into what TIA 568C is calling out for standards. And then I'll highlight some best practices and things to help you be able to implement those standards. And then we'll wrap things up with spotlighting some requirements that you'll want to keep in mind when you're looking for tools to help you achieve those standards that are being called out. Starting off here with fiber optic connectors. This is just a brief overview. We all know and love connectors in any enterprise application because of the benefits that they give. You have the ability to add, move, drop things from your network, and just the flexibility that connectors give you is what is a real benefit. This pertains to both copper and fiber connectivity, but with the transition to fiber optics becoming seeing more and more presence in an enterprise, there's certain things that you want to keep in mind, particularly when dealing with fiber optic connectors as it compares to copper connectivity. In addition, fiber optic connectivity is transitioning beyond just inside buildings. We see that now in other applications, whether that be fiber to the home or fiber to the antenna. We realize that many of the technicians today who are working in enterprise environments are also working in a lot of the new and emerging small cell or fiber to the antenna environments as well. So these kind of practices that we're highlighting today are also applicable in those places. Brief spotlight of when we're talking about a fiber connector, what are we really looking at here? As you know, light is transmitted from the core of the fiber. And if you ever have held a fiber connector in your hand and look at that, a common mistake is to look at the little ceramic white piece in the center and assume that that itself is the fiber cable, and that's actually just a part of the fiber connector as a whole. The fiber itself is a very small piece located in the very center there. What you're looking at is the ceramic ferrule, and the purpose of that is really to hold the fiber in place. At the very center of that, it's very small. I would dare to say on the verge of microscopic, but a lot of people, if you look at that just right, you can actually see the end of the fiber at the very center of the ceramic ferrule. But at the very center of that fiber itself is the core, and that's where the light is actually transmitted. In this diagram here, it actually shows the fiber protruding from the ferrule. I did that strictly for illustrative purposes, just to give you an idea of where the fiber is located. Here's an interesting view as well. If you want to see what the fiber actually looks like, you really are going to need a microscope. This is a view of a fiber interface through a microscope. The white area around the outside perimeter is the ceramic itself, and then that gray circle, that's the fiber. That's the fiber itself. The gray area is what's referred to as the cladding. That really holds and protects the core of the fiber, which is at the very center. In this example here, I'm showing a single mode fiber, which has a 9-micron core. You'll also see multi-mode fibers, which have a slightly larger core, being either 50 or 62.5 microns. Hopefully at this point the terms that I'm using are things that most of you may be familiar with, but I wanted to just review those because we're always getting new technicians into the industry, so it's good to give a recap of this. Another thing that's really common in the enterprise is two different kinds of fiber connectors. There's the ones that have single fiber, like what I had described a minute ago. That's where you have just one single fiber per connector, and you'll see the ceramic on the outside perimeter, and then the fiber in the center with the core in it. Again, this is a single mode. Common types of those in the enterprise include the LC, which is shown here, and the most common one is actually the SC connector. Other ones that you may see in the enterprise are an FC, which are not as prevalent anymore necessarily, and the same goes for ST. There was a time about 10 years ago when you saw a lot more of those than you do today, but the most common today are the SC or the LC, which gives a little bit more high density. And then contrast that with the fiber connector on the right, which is a multi-fiber connector. These are really interesting in that they give up to 72 fibers in a single fiber connector. The amount of fibers ranges. It can be as minimal as 8 connectors, and it jumps there from 12, 24, 48, all the way up to, like I said before, 72. And they literally just lay out rows of fibers inside this ferrule. This screenshot here shows it's just a brief snapshot showing 3 fibers in an array. That actually has, I think, about 12 in that particular array, and then there's multiple rows of 12 shown there. Notice that the outside perimeter of that is slightly different than the white ceramic on the single fiber connector. That's just because the material that's used in the multi-fiber connector is a combination of polymer and ceramic combined, so it looks a little bit different than what you'll see with just all ceramic. And the common types there really are the same connector type. They're oftentimes referred to as either MPO or MTP, which is a brand name in the industry. Again, I just reviewed some of the common types of single fiber connectors. I mentioned here's what that SC looks like right here. Again, the last page showed the LC over here. That's the small high density one. And then up at the top are the FC and the ST. Just a brief highlight, the LC does have a smaller ferrule than the other ones. You'll notice all these other ones here have a 2.5 millimeter ferrule. But the LC uses a 1.25, and you can actually see this right here. If you look, you can see there's the ceramic ferrule. You contrast that with the 1.25 millimeter ferrule on the LC, and I just wanted to highlight that because oftentimes when you're handling these, the 1.25 millimeter ferrule is a lot more fragile, so you got to take extra care when you're handling those. So how does a connection work? A fiber connection is the concept is somewhat similar to a copper connection, although with a copper connection, you'll usually refer to 2 different parts, either the jack and the plug, which physically actually have a different look to them. But with fiber connectors, the connector on the front and the back actually are the same. Typically, they're just joined together by the means of a bulkhead adapter, which has a mating sleeve or an alignment sleeve in that. But when you're typically seeing that as a technician from the front of the patch panel, you won't see the connector necessarily behind it, but what you will see is a bulkhead port. So what I've shown here is a cross-section of what that connector behind the bulkhead may look like. You'll notice that there's the ferrule inserted into the bulkhead, and there's an alignment sleeve here that's properly holding that ferrule in place. It stops it at the right point, and it aligns it in the correct position so that when the connector that you're plugging in comes in, it's properly aligned. It makes physical contact with the other end face, the ferrule end face of the other connector, and it's able to pass the light through. So if anything happens to that physical connection there, the integrity of the connection is going to be compromised. And so that, speaking of compromising the integrity of the connection, I wanted to highlight particularly some issues as it pertains to contamination of the fiber end faces. And the reason why I particularly wanted to focus on this is because it's the biggest cause for network failures today. What I have here up on the screen is some statistics that were taken from NTT Advanced Technology. As many of you guys know, they're a leading company in the industry with fiber optic technology. They're out of Japan. They're a service provider over there. They're sort of the AT&T or Verizon of Japan, or you could even say that it's all of those combined. So they really have a lot of knowledge, and actually the SC connector that we know today was actually invented by them, so they know a lot about fiber optics. This study, as you can see here, has some really interesting data points. They asked the question to both network owners and installers, what are the biggest causes they've seen for network failures? And the feedback varied slightly from the network owner from the installer, but the #1 response that people gave back for causes for network failure, I'll highlight this here at the top, is contamination on the connector interface, end face. You can see here that when it came to installers, 98% of them responded back saying this is the biggest cause for network failure that we see. To highlight that just a little bit more, if you look farther down, another response that people gave was damage on the ferrule end face. So you could really kind of pull from that these two, there's a correlated relationship there. Oftentimes the damage on a ferrule end face is the result that started from contamination on the connector end face. So these are two of the leading issues in network failures that are seen today. And I particularly wanted to highlight this too because you notice down here at the bottom, one of the statistics here is excessive bending for the cable. Now granted, the technicians, our installers, are still seeing over 60% of problems associated with that. But then once the network is installed, bend radiuses and such are properly maintained, and so now in those situations, less than 10% of the time those become issues. I wanted to contrast that with something like contamination on the connector interface, where you see obviously nearly every single installer deals with it, but even after your network is built and it's handed off to your network owner, the network owners, the problem doesn't go away. It's still 80% of the time they're going to have to they're dealing with network failures that are caused by contamination. So for both network owners and installers, contamination on the end face is the biggest cause for network failure, which is why we're talking about that in this presentation today. So with that, what makes a bad connection? I first wanted to just highlight what the attributes are that you look for in making a good connection. #1 is physical contact. I highlighted that in one of the previous slides, showing those two end faces making physical contact. The next one is proper core alignment, and really to achieve that, you just need to be using a good quality bulkhead adapter with a quality mating sleeve. Now I highlight that today, even though I highlight that today, it's pretty much taken care of by the manufacturers these days. The quality of the components these days are much better than they were, let's say, 10 or 15 years ago. But that's a key attribute to making a good connection. But the third attribute to a good connection is a pristine end face. And I called this one, what makes a bad fiber connection, because with contamination, if you introduce dirt into the end face of one of the connectors, now you're compromising the integrity of the physical contact that occurs. So therefore, now you're not going to be able to effectively transmit your optical signal through that connection. In addition, you're also not just going to compromise the integrity of the connection. You'll also run the risk of damaging the end faces of your connectors, which means you'd have to then do some troubleshooting and possibly replace those connectors. So where is this contamination? Where does this exist? The short answer for this would really be everywhere, but I want to give a little bit more specifics to you guys on what you should be mindful of when you're handling the connectors. Because I work for a company that manufactures and builds test equipment, I highlighted test equipment as the top one, mainly because we see this all the time. I could tell stories that we see from our service department where someone will send back a very precision advanced piece of test equipment like an OTDR or something for service, and our service department will, after assessing it, will then determine that the service that it needed was that the fiber connector on the test port was severely damaged because people were plugging in contaminated connectors into it. So they would deal with that and send it right back to the customer. So I highlight that because a lot of these pieces of test equipment you're investing a lot of your money into these, and so you'd hate to have a problem with one of your big investments simply because you weren't maintaining the integrity of the connections on it. The next one is kind of the old adage that people always talk about with dust caps. You hear everybody talking about how dust caps really aren't intended to keep the dust away. They're more just protective caps. They're not a end-all be-all for solving the problems of keeping your ferro interface from getting dirty. In fact, there's several situations I can tell you where a manufacturer has properly built their patch cord and sent it off to someone to be used, but in the process it sat in a warehouse for a while. The different temperatures have fluctuated, and it's almost like that little space in there is a microscopic greenhouse, so that when you unpackage that connector, take the dust cap off, and you look at it through a microscope, you can see all sorts of different things that may have developed in there, particularly as it pertains to condensation or mold and such. The good news is that by following some proper best practices, that can easily be removed and dealt with. So it's not a catastrophic problem if you're proactively dealing with it. Bulkheads. This is another really important one, mainly because I want to highlight this for those of you in the enterprise, because many of you, when you're dealing with fiber inspection in the past, when I asked you if you have a microscope, they say, yeah, I always inspect my connectors. I have a little microscope that came with the kit that that I bought with my fiber connectors, and I always check that before plugging it in. But I just want to highlight and caution you on that, because there's two sides to every connection. So if you're only just checking the end face of the connector that you're plugging in on the male side, the patch cord side, you're missing the other half of the connection. And if there's contamination on that other side, plugging in a clean connector into that is going to have just as much impact on that connection, because one half of it was already contaminated, and once you plug that in, you're actually going to be transferring that connectivity or that contamination to the other side of the connection as well. The next one sort of goes without saying, but people are a big source of contamination. If you've ever handled these connectors, and accidentally touched the interface of one and then looked at it through a microscope, you know what I'm talking about. You see firsthand just kind of how easily a fiber interface can be contaminated just by accidentally touching it with your hand. The third one, the last one, the fifth one, is the environment. Oftentimes in enterprise situation, you could be in a new construction environment, so the telecommunications room that you're in isn't necessarily all set up for being completely pristine and clean and airtight and dust-free yet. You could be dealing with all sorts of residues. So but that applies for both in buildings and also out of buildings, especially in outside plant applications. Dirt is everywhere, and these are just 5 examples of some specific things that you should be mindful of when you're working with fiber connectivity. And so when we're talking about contamination, you saw in that slide before talking about biggest problems with network performance. How specifically does dirt correlate with impacting your network? And hopefully this slide could shed a little bit of light on that. What I'm showing here on the right is a screenshot from an OTDR. As many of you guys may be familiar with, an OTDR will measure the loss of an optical signal as it progressively travels down the path of your optical network or your channel. And every time you see a little spike, that means, like this one here, that means that there's an event that it noticed there, a reflective incident. And you'll notice here I put a couple numbers above some of these, and I included some screenshots of some of those numbers of the events. The first one here is of that small spike is an event that's caused by just a fiber connection. There's 2 fibers mated here, and you're always going to see a little spike whenever that happens. It's actually factored in. In fact, even when you're budgeting the loss, now typically the typical loss budgeted is about ½ dB, just specifically for a mated connection. So that's factored into it, into the budget, so you will see a little bit of a spike. In this case here, you see that there is a little bit of a back reflection, and the loss here is about 0.25 dB for that particular connection. And I included a screenshot on the left of number 1, and you can see that that's a clean connection. Now, as I go further down this trace here, I didn't include a screenshot of number 2, mainly because it's also a clean connection, so it would be basically looking the same as connection 1. But I want to highlight the event here, number 3, because you can see that spike is significantly larger, and also the line dips significantly lower than before. That's the loss of that connector. The back reflection on that one is significantly higher. It's actually about 32 dB, but the real thing that I want to highlight here is the loss of connection 3 here. You see that one here, the loss marked in that red box there is 4.87 dB. And again, going back to when if you're factoring in your budgeted loss of ½ dB per connector, and you've got one connection point here that now is experiencing almost 10 times your budgeted loss, that's a real cause for concern. You ate into a lot of your loss budget, and it could be, in the end, it could impact the performance of your network to the point where it's not going to work. And so now I included a screenshot of what one of those fiber interfaces looks like, and you can see here it's a dirty connector. There's little fragments of contamination here or there, but I particularly want to just highlight, if you can see at the core of the fiber there, at around the 2 o'clock area, there's a small particle that's partially blocking the ferrule, the core of the ferrule there, of the fiber, and that's likely the cause of that 5 dB loss. Now just bear in mind here that the core of that fiber is 9 microns, and that particle there is probably about less than half that size, so we're dealing with a 5 micron particle here that landed on the core of that fiber. And so we're talking about here a microscopic 5-micron particle now taking your network down. And so, as I like to say, kind of welcome to the microscopic world of fiber optics and the problems that come with them. Obviously, we love fiber optics, but these are the kind of things that we need to be mindful of when we're handling them. So, somebody may look at this and say, well, hey, if the debris here that's on the core is the real cause of the problem, why should I care about any of this this other debris that's around the outside of the area? And a good example that I give people here is this here I call the illustration of particle migration. I do a couple screenshots here of showing first a connector that has a few particles that aren't really on the core. It shows, you can see I showed 3 fairly large particles somewhere out on the cladding of the fiber. But then I mated that connector and I looked at it again through a microscope. And hopefully you guys can see there, the next screenshot shows that those 3 large particles that were on the cladding of the fiber basically exploded and sent shards of that microscopic debris all throughout that connector. I mated it again, and it got worse, and then a third time. And in this particular instance, now you can see that the core of that fiber is completely blocked. Now, there's no guarantee necessarily that the debris is going to go specifically into the core of the fiber. It's going to go anywhere. You can't control where it's going to go. But the point of this was really to show that even if you don't have the debris on the core of the fiber, when you mate that, you still run the risk of potentially damaging the performance of your network, because it could send that debris all throughout that fiber interface, including the core. So therefore, you do need to be mindful of the debris, not just on the core, but in other places of the fiber interface as well. This here is a image that was provided to us by our friends over at CommScope. As many of you guys are familiar with plug-and-play cassettes, I highlighted earlier in the presentation the MPO or the MTP type connectors, which include multiple fibers in a single connector. And so when you start thinking about dirty connector interfaces, now think of that in perspective with in relation to a MTP or an MPO connector. If you have one of those that happens to be contaminated, now you're not just taking down one single fiber throughout the channel. You run the risk of taking down multiple, up to 72 actually. And this example here gives a good illustration of that here as the signals are being sent down the network. I particularly spotlighted this MPO MTP connector on the back of one of these cassettes. If that happened to be contaminated, now everything that appears after that gets taken down. So you can see the impact of some microscopic debris on a connector interface really can be exponential. I can share some firsthand stories here about people who have experienced this, and the real downside with this is once you discover it, it's oftentimes, I don't want to use the word too late, but it's usually when the network gets fired up at that point and they realize that an entire wing of your building isn't coming up. So now in order to deal with that, everything needs to be shut down again, and you need to do some serious troubleshooting and repair to get that back up. So it's not just taking down in that situation the connectors that weren't working. You might have to take down all sorts of other areas as well to deal with the troubleshooting. So you don't want to be that technician. So with that, this is a good transition into where I really want to focus on today, and that's best practices and standards when it comes to handling fiber connectivity. The rule, or the old adage that we like to use at JDSU, is a term that we call inspect before you connect, or the inspect before you connect process. And you can see it being animated here on the screen as I'm talking. It starts here up in the left-hand corner, where the very first thing that you want to do is, first and foremost, inspect. The reason I say that is because there's a mentality in the industry that people think, well, I just need to clean them. I need to clean them. You'll hear that term a lot. You know, make sure that you're cleaning your connectors. And that is very true. Part of the inspect before you connect process does include cleaning if it's necessary. But it's sort of like if you're not looking at the connector, if you don't know what you have on the end face, then you're sort of flying blind. You may have a clean connector already, so you don't want to unnecessarily run the risk of cleaning something and risk potentially damaging it or adding contamination to it if it's already clean. The other reason that this process highlights is that after you clean something, how do you know it's clean? You need to be able to check it after you've cleaned it to make sure that you remove the debris. This is particularly important if you're dealing with a situation where you've already connected a dirty connection and now you're sort of in troubleshooting mode where a lot of that debris may have been embedded into that glass end face, and so it's not necessarily going to come off with just a one swipe cleaning approach or something. And so the process, as you can see here, is inspect it first and ask that question, is it clean? It'll either look like this one on the right, which is clean, or it'll look like some variation of this one here on the left. So if it's not clean, then clean it. But then afterwards, check that again and ask the question again, is it clean? Now different companies may have procedures for how many times you go through this loop of cleaning and inspecting and re-cleaning again before you just decide to cut that connector and re-terminate. But the process, the universal process does remain applicable to all situations here, so that once it is clean, then you can finally connect that. One thing that I also want to highlight here, and I talked about this before, is this process applies to both ends of the connector end face. So don't fall into that trap of just checking your patch cord before plugging it in. Make sure that you're checking the connector behind the bulkhead as well. The pictures here show an example of what that looks like. The picture on the left shows a patch cord being plugged into a microscope that has a little video display on the screen. So you can plug that into the adapter and look directly at the end face of that patch cord. And then also the picture on the right shows what it looks like to inspect the connector located behind the bulkhead. You notice in order to do that, you need a special, what we call a probe microscope, that allows you to insert it right into that bulkhead and get a view on your screen of what that connector behind the bulkhead looks like. Again, by doing this, it allows you to inspect both ends of the connector interface to make sure that your connection will be free of defects. I highlighted before that MPO, MTP connectors as well. Oftentimes you'll see this in those cassettes. And the thing that I really want to reiterate here is that because an MPO has multiple fibers in a single connector, you want to make sure that you can effectively see every single one of those fibers. So you can see here on this picture, there's a special tip on the end of that microscope, that probe microscope, that allows you to do that. It inserts directly into that bulkhead, and there's actually, you can see a wheel dial there that as you turn that, it'll scroll the camera so that it'll enable you to see every single one of the connectors, both horizontally and vertically. There's actually two dials here that control the X and Y axis for inspecting those end faces. Proactive versus reactive inspection. This is a really key issue that I want to highlight, mainly because inspection can oftentimes be viewed as a troubleshooting method, which means it's done after you've connected everything, and then you activate your network and you run your OTDR trace or whatnot, and you find that there's a catastrophic event somewhere, and you isolate it down to a connector somewhere that turns out to be dirty. But by that point, you've already mated that connector, and you've already likely embedded debris into that. So I want to contrast that proactive versus reactive inspection. Here's a picture of a connector, fiber connector end face that has a significant amount of debris on that, but it hasn't yet been mated into another fiber connector. And so if you see that debris, if you proactively inspect that, if you go to clean that, it comes right off because it's basically just resting there right on the end face of the connector. But if you're dealing with a fiber that you're inspecting after it's already been mated, here's an example of, again, starting off with a clean connector. But in this case, I then took that connector and I mated it to another one and then tried to clean it after decoupling it again. And after I cleaned it, this is what it looks like. You'll notice that I was able to remove a significant amount of the debris, but there's a lot of small particles that ended up getting embedded right into that glass. Particularly if you look even at the core, there's a couple of small particles there, right where you don't want them to be. And so now in this case, even though you cleaned it reactively, and when you inspected that, you saw that that's not likely going to be coming off. And even if you are able to remove the debris, likely pits and chips will remain behind. So I just highlight some cleaning materials here. There's a lot of different tools that exist out there. I encourage you to use them. I stand by all of them. The key that I'd highlight there is just to make sure that you're doing it. It's part of your process. I'd be a little bit mindful of swabs just because they're a little bit more craft sensitive, but there are some things out there like some of these cleaning tools that you see in this picture here that really automate the process and take a lot of the craft and skill out of it. So those are really nice. Also just highlighting there's some solvents here and such that if you got some stubborn debris, things like that can be helpful. But I would just, my recommendation is that if you do use a solvent, follow that up with a dry cleaning process afterwards so that you can help remove some of that solvent as it evaporates and just kind of remove some of that. So just a real quick recap here, some of the benefits of proactively inspecting before you connect. You're reducing that downtime, you're reducing the troubleshooting, you're optimizing your signal performance, and you're preventing network damage. You've invested a lot, or your customer has invested a lot in their network and their fiber infrastructure, and following these best practices really allow them to get the most out of that. And this is something that, as I've been talking about here, over the past several years, this is something that's really taken on a lot of recognition in the industry to the point where standards bodies have got involved. And I want to particularly highlight the starting with the IEC 61300 standard, 61300 and 335. This was released coming up on 5 years ago now, and what this was it was a means, just like any standard, it was really intended as a common reference between suppliers and customers or between work groups to ensure a level playing field with what people should expect when it comes to an end face and how it should look like in terms of cleanliness. For more information on that, we do have JDSU has written a really comprehensive white paper on the details of that standard and how you can achieve that most effectively. And a lot of the things I'm talking about today actually are highlighted in that as well. Just a brief overview of how the criteria that the IEC put in place. What they did was they took different kinds of connector types, whether that be single mode, multi-mode. They actually have one for single mode APC, one for single mode where you have a better return loss numbers. And they also have one specific specs for MTP and ribbon requirements as well, MTP, MPO. And in each situation, what they've basically done is looked at an end face of a connector and divided, I shouldn't say divided, but broken it up into a series of concentric circles that they refer to as zones. And each zone, as it gets closer to the core of the fiber, has more and more strict criteria for the allowable amount of both scratches and defects. And here's an example of one of those grids here on the left. There's 4 zones. This one here is what's called the single mode UPC standard, or greater than 45 dB of loss. Zone A is the core. In this situation, they've identified that no scratches or no defects are allowed. I'm going to skip past Zone B and go to Zone C, which is called the adhesive zone, which is basically it allows anything in there. Basically, this just creates a little bit of flexibility for adhesive on field terminated connectors and such. And then there's the contact zone way on the outside that allows for, hey, you can have some debris out there, but nothing larger than 10 microns. But then if you look at the cladding zone, this is really kind of the danger area, in that you can see it says, hey, no limit for particles less than 2 microns, but nothing larger than 5 microns. But then if you have particles somewhere between 2 and 5 microns, you can have up to 5 of those. And so probably even as I say this, it starts to sound a little bit confusing. But the purpose behind that is these are based off of a lot of study and research that went behind this to determine, what is an acceptable level of contamination that could be on an interface to still be appropriate. But it is a bit of a challenge to try and evaluate this. I mean, you start asking the question, how big is a 6 micron particle versus a 4 micron particle? Or how do I know that I'm in the cladding zone versus the core zone just by reviewing that? And so it can really become subjective. So that picture there on the lower part of the screen shows that. It's, looking at this connector here, I can kind of see that there's maybe a few particles there, but how big are they, and what are they, in the zone B or zone C? I can't tell. And so if you use objective inspection, this is where it makes it a lot easier. And when I say objective inspection, I mean using the benefit of automated tools that can actually analyze, capture the image, analyze and characterize the interface, and actually report back to you with an automated process what defects and contamination are on there. This is a screenshot here that was taken from one of those tools, and you can see it actually provides the zone overlays for you, and even more beneficial than the zone overlays, it actually identifies the different defects that are on there and characterizes them by the size. So in this case, it found various pieces of contamination that were highlighted blue, which means, hey, that's acceptable. But then you look down here, right around 12 o'clock, there's a red debris particle there that was larger than 5 microns. And so there, as a result of that, this connector failed because it didn't meet these criteria. But without the aid of an automated objective inspection tool, it can become a bit challenging, and we recognize that. So how is the IEC standard used? Really, it levels the playing field. Before standards like this standard existed, there was a lot of confusion and frustration when it came to customers and suppliers. A supplier would ship something off that they felt met their criteria, but when the customer received it, they felt that the criteria that they were evaluating it to, it didn't meet their standards. So everybody had their own standard. And so by the IEC coming out and releasing something, it really gave something, a common reference tool that suppliers could give to their customers, saying, hey, we meet this standard. It's also something that a customer could put in their job spec and say, here's something that we'd like for you to be able to achieve in the product that you deliver to us. So where is this used? Frankly, it's used throughout the entire fiber optic product life cycle. But I do want to highlight a few in particular that pertain to the enterprise, and specifically how it plays in with the new TIA 568C standard. Last summer, the TIA 568C standard was updated to basically call out and reference the IEC standard. So there are several places now in 568C that directs people to the IEC standard. So as many of you know, in the enterprise environment, TIA 568C, in their own words, it is the foundation for premises telecommunications cabling infrastructure. So there's requirements there for both twisted pair and fiber. But last August, it was updated with some addendums and such that particularly address end-phase conditions. And so there's a few places that I just wanted you guys to be aware of. One is Annex E. That's at the end. It's an informative guideline section that really is intended to clarify the processes. I don't know about you, but whenever I read through standards documents, oftentimes it's very dry reading, and it can oftentimes leave certain things up to asking the question of, well, how do I do that? The Annex E is a place in 568C that gives further specification and clarification for how you do that, particularly how you do perform fiber optic testing. And so it calls out some specifics with regards to the procedures you should use and also the tools that you should be using. And so here are a few excerpts of what that means. In general, they identify that microscopes and cleaning materials must be used. So there's a few things that I just highlighted in here saying, hey, you need to be using an inspection microscope. You know, the term ensuring that it's clean doesn't just mean holding that connector up to your eye and looking at the end face and saying, yeah, I don't see anything on the end face there. You need to use the proper tools, and so they're clarifying that. They're also saying that both the test jumpers and the ports need to be in accordance with the IEC standard. And I just want to reiterate here, they're saying both the test jumpers and the ports. So that means your bulkheads and your patch cords. So don't fall into that trap of just making sure your test jumper's clean. Third is that it requires the end-face requirements need to be in accordance with IEC. Again, the term IEC 61300-335 shows up in multiple places now in the 568C standard. And then last, it requires that connectors should be inspected every time before testing. So when I saw this, I was really encouraged because it was very much in line with, you know, we always talk about with proactive inspection. It's saying, hey, just like that network installer who inherited the network owner who inherited the fiber network and the connectors from the installer. Contaminated connectors continue to be a problem because every time you handle that connector, it runs the risk of being contaminated again. So you need to be mindful of that and make sure that you're inspecting them every time before you test. So I just highlighted a couple of those words to be mindful of. I also wanted to just reiterate that in addition to that, there's a couple of FOTPs as well that's referenced, particularly multimode is 526.14b and single mode is 526.7. Both of those also include language now that pertain to end faces need to be in accordance with IEC. I included some of the verbiage here, just some snapshots of what that looks like. They also now call out that you need to be using a microscope, and furthermore, that microscope needs to be using the adapters that are compatible with the connectors. You remember earlier on in the presentation when I showed the example of when you're inspecting a MTP or an MPO connector, you needed a special adapter on the end of your microscope to be able to do that. What they're saying here is, you know, make sure that you use that right adapter. Use an APC type adapter or a tip if you're inspecting an APC connector and not a regular one. And so with that, a good transition into some of the tools of the trade that you need to be mindful of these days. There's a lot of good tools out there, you know, whether that means you need a microscope, you need cleaning supplies, you need a power meter, you oftentimes will need a visual fault locator. But the common response that I get from people is that, you know, it's just too many tools to handle. Oftentimes my technicians aren't doing this mainly because it's a real mess to try and do all this kind of stuff, and it ends up looking kind of like this guy here on the right, just trying to hold a bunch of stuff, and it just seems to be a mess. The other barrier that oftentimes people will indicate is that it just takes a long time to do all this. It's time consuming to follow best practices. I mean, when you go through, I'm just kind of breezing through really quick. The proper methods and procedures to follow. In the end, it could take upwards of 2 minutes or more for even a skilled technician to do one of these things right. And so that's kept a lot of people away from following these best practices. But now we're at a point where it's no longer just a best practice. Now this is something that's included into 568C. And I've actually talked to a handful of design engineers now who are, when they're writing their job requirements, they're fed up with the issues that have been coming up that they've been dealing with connectors being contaminated and impacting the job performance. And so they've written in language pertaining to inspection and such into their jobs. Now they're taking that a step further and saying, hey, you need to comply to what 568C says. They were already referring to 568C, but now that's folded into the language, they're specifically highlighting that in their job requirements. So with that, just a few things as technicians that you guys should be mindful of when you're choosing tools. Number one, choose tools that drive behavior for best practices. Those tools that I showed you before, they're sort of yesterday's tools, if you will. You want to have something that is easy to use and it's fast. It allows you to really achieve a smooth, seamless workflow that incorporates into what you're already doing. You like to have something that you use anywhere. Portability is key, so you don't want to be able to be lugging around all sorts of junk on a cart or something, or you don't want to have some real big, heavy, kludgy thing. You need something that's really fast and efficient and portable. And finally, you want something that I really recommend something that allows you to prove the quality of your work. This is something that a lot of design engineers are also now requiring. Is they're saying, hey, we want to see proof that you comply to the 568C standard. And how you can do that is there's tools out there. I talked a little bit before about objective inspection tools. One of the nice things with objective inspection tools is there's some perks that come along with it in that it allows you to capture the interface of the connector. It allows you to, it'll drop in the overlay of the zones and also the defects and the contamination. It'll give a pass-fail report on that. And you can print out certification reports or create PDFs so that you can provide to your customer in the end the proof that the work that you did and the job that you accomplished is in compliance with 568C. And just a real quick thing as I wrap up here. Here's an example of something that my company JDSU has come out with in the past couple of months. It's our Smart Glass Fiber product family. And what it's really trying to do here is take all the common things that a fiber technician does on a daily basis and fold it into a tool that allows you to do this seamlessly and easily and portably. Many of you may be familiar with the tool that we have right now that incorporates a power meter with a microscope, and it really, the feedback that we've heard from people is that it really is a game changer for technicians. It allows them to do things fast. It allows them to do things quickly, and it's portable, and it drives their technicians ultimately to do things right. This is taking that same step to the next level. Now it's giving you the ability to do that pass-fail analysis right on the device, so it's really easy to provide that certification that you're looking for. Here's how it does that: is it uses what's called our P5000 iProbe microscope. It's a digital microscope that actually plugs into not just our Smart Glass Fiber family, but also any other JDSU devices that you have. So if you have one of our OTDRs or any of our maybe our access devices and such, it'll work on there as well. And here's an example of what one of those certification reports looks like that you can hand your customer. The benefits of that obviously is that you can work a lot faster. That process that I described earlier of over 2 minutes here, that's kind of the old way of doing that. You contrast that here with even a new technician can do it in less than a minute. We've got people who, even after limited exposure to this tool, are able to do an entire cycle of a connector and certifying it and taking the power measurement and everything in 30 seconds. So a real benefit contrasting 30 seconds versus 2 to 5 minutes per connection. So just in closing, fiber is expanding everywhere, deeper into our networks. Contamination, as you saw, is the #1 source of troubleshooting. And now with the IEC standards being incorporated into 568C, this is something that technicians in the enterprise really need to be mindful of. Not just mindful of, they need to be able to, they need to be addressing. And so it's really critical that you follow these best practices, and we highly recommend that you use the right tools to be able to achieve that effectively. And with the right tools, we're confident that your technicians can be fiber smart. With that, we've got a few minutes left. I did want to open it up. Karen, I'll hand it over to you to address any details as far as handling how Q&A will work.
You bet. Thank you so much, Tyler. Great information here, and we're getting a lot of great comments that have come in. This is Tyler's last slide with a great summary here, and we do have the opportunity for folks to ask any questions. You'll see in the lower right-hand corner of your screen is the Q&A box, and in this box, please insert your questions there. That way Tyler is able to see those, as opposed to in the chat window. That'll help us to make sure that we can get those answered for you. So with that, we can start with the Q&A window itself, and again, if you have inserted something in the chat window, if you wouldn't mind just inserting that same information in the Q&A box below, then we can get that to you. Tyler, would you like me to read the questions, or do you want to go through those yourself?
Actually, yeah, I'm seeing them right here, and I can just jump right in and answer them. Some really good questions here, you guys. Good group. First one here is IEC 61300-335 seems to be the current standard that defines the common set of requirements for interface quality. Is it so, or are there other standards? And hopefully, this question I saw was actually asked at the beginning of the presentation. Hopefully this addressed a little bit of that already, but there are, in the presentation today, I talked about 568C adopting the IEC standard. And that's actually true for most situations, actually. What we're seeing is that other organizations are looking to the IEC standard. They were the first one. They were the ones who spent the, hundreds of thousands, if not millions of dollars with people to try and to develop that standard and release it. And so a lot of people are in their own standards, just referring people to IEC. Now there are a few variants of that. I know that there's some mill specs that have been in the works for a very long time, and they wanted to have something a little bit different than the IEC standard, and that continues to kind of go through some changes, and so it really hasn't been completely finalized. But aside from that, most people are actually using the IEC or maybe a subtle variant of the IEC standard. Another question here, sometimes I cannot see the fiber core when viewing. Why is that? This happens even on a small length where I would think that I should see some light. Good question. This goes back to, it really, you talked about the, even on a short link. Technically, I actually don't really, it's not necessarily mandatory to physically see the light coming out of the fiber core when you're inspecting it. Oftentimes in the screenshots that I show in these presentations, I will deliberately hold the other end of the connector up to a light so that it gives some kind of light purely for illustrative purposes so that people can see where the fiber core is. But depending on the connector, the fiber type, it really depends on the attributes of the fiber. I've noticed that sometimes you see that the core being more illuminated than other times. I've even seen this on even a patch cord where you may not see an illuminated core. But the important thing there is that when you're inspecting a fiber, seeing the illuminated core isn't really as critical. But where it does become a bit more of an issue is when you're trying to adhere to that IEC standard, and this is where it becomes a challenge because how do you know, where 9 microns or 25 microns away is relative to 45 microns. And so when you're using something like one of those objective tools like the P5000i, all you do is just press a button on the microscope, and the analysis will begin. And it will give you that overlay of where the core zone is, if you will, and it'll also give you the identification of any defects in there. So that will basically identify the physical location of where the core is for you. Another question here. Other than dust caps, is there any other way to prevent contamination from the manufacturing plant? You know, dust caps is really par for the course. You need to do that. I've been into a number of facilities that are manufacturing cable assemblies, and oftentimes those rooms, 90% of the time, I should say, they refer to them as a clean room. So there's special HVAC systems in there that are really keeping any airborne dust out of that area. But the thing that I'd want to highlight there is that for the most part you can pretty much be confident that the patch cords that you're receiving are going to be in, they're not going to have embedded debris in them per se, but my recommendation is no matter what, you always need to inspect that connector of the patch cord after you receive them, because it could have left that facility perfectly clean, but like the example that I gave, you know, it could go through all sorts of environmental changes when it's, or temperature changes when it leaves from the time it left the facility to about the time it reaches the end user's hands. And so if you inspect that and if you find anything on there, you can proactively clean that. If you reinspect it again, you can pretty much guarantee that any debris that may have developed on there afterwards has been removed since then by cleaning it. Let's see, another good question here. Can a clean connector become contaminated just by inserting it into a bulkhead that was inspected, or can they become contaminated over time? Oh, good question. So if the bulkhead is clean, if you've got a clean patch cord and a clean bulkhead, if you insert that and make that in there, it will pretty much, that core now is making physical contact. So if you had clean fibers before they made physical contact, nothing's going to get in there, with the exception of, let's say there's the occasional outside plant situation where a connector that is in a box that's at a ground level or underground or something, and there may be water that gets in there. So things like that could find their, potentially run the risk of creeping in there. But once those connections have made physical contact and it's clean on both ends, you're really in good condition. It's not going to, even that scenario that I gave was a real outlier, and especially in enterprise, you're not going to see that. So once you've validated that you've got a clean connection on either end, I like to say at that point, you really have a good lifetime connection there. Can debris still get through the bulkheads? I'm not sure if I understand. That could mean a couple things. Does debris, I will say, can debris still get into the bulkheads? Absolutely. That happens all the time. Can debris make its way through the bulkhead just by airborne kind of whatnot? Possibly. I think anytime you've got a connector that hasn't been mated, that bulkhead, you should check it. And if it hasn't been mated, it's likely that if there's any debris that is on there, you'll be able to remove it right away. So again, as long as you're it doesn't really matter how necessarily it got there. It could have gotten there by the dust cap on the bulkhead, or dust just making its way in there. But if the mentality that you have is the very last thing that you do before you connect is inspect that you're checking that right before you connect it. So that's the very last thing that you're doing before you make that connection. That's really the most important thing, so that you're ensuring it's clean before you connect it. Let's see, a couple more questions here. We're already running over. We deal with network technicians here. Would you recommend that they purchase and learn to use the equipment you displayed? I might be the wrong guy to ask that because I would definitely recommend our stuff. But however, you know, we, as a product manager, we've put a lot of thought into this, and we've been dealing with this for years. And we try and we develop these tools specifically for the purposes of making life easier for people. We know that, you know, the analogy that I always give is it's like, fiber inspection is sort of like having a healthy diet and exercising regularly. We can all sit here in this group and agree that it's a good thing to do and we should all be doing it, but getting everybody to do it is another challenge. There's different reasons why people don't do it. And so when we developed the tools that I highlighted in the presentation at the end, our number one goal was to be able to overcome those barriers. We know people need to do it, but we're trying to now make it easier for people to do that. So, and this goes along with a underlying theme or an overarching theme that JDSU is taking with our tools of making it easier to do the job right. At the end of, you notice at the very last bullet here on this summary, I say, with the right tools, anyone can be a fiber smart technician. You know, our goal here is to be able to give your technicians, you know, with our tools, by using our tools, your technicians, even if they're fairly new, our tools are easy to learn, easy to use, and gets them up to a level that's expected of them in today's environments. And with that, I know we've got certain questions that are continuing to roll in. One last question here. What are the best methods to clean fiber in the bulkheads without removing the fiber connector from the bulkhead? I think what you're saying here is, if you got a connector located behind the bulkhead, how do you clean that? That's a great question. Oftentimes in the enterprise, sometimes the technician may have access to the connector in the back, and so if you do that, you just walk to the back side of the patch panel and unplug it, and you can clean that. But that's now basically easy access to the connector, and you unplug it from the bulkhead and plug it back in. But more often than not these days, especially with things like those MTP cassettes, where they're fully enclosed, you don't have access to that connector, quote, behind the bulkhead. It may be inside that little cassette. And so you may remember that in the cleaning tools slide that I highlighted, there's a lot of different things. There was a series of, starting with swabs and then going into a whole array of different cleaning tools made by a number of different manufacturers that are these little cleaning sticks, click style tools, where you can actually take the clicker, and it's got a movable thread or a cloth on the end of that, and you can actually insert that stick right into the bulkhead and either push a button or apply pressure to the stick, and it'll actually move and rotate that cloth to effectively clean the connector that's located behind the bulkhead. So it's actually a really effective tool. We don't make them at JDSU, but we like them so much that we actually include them in our kits as well. We've got a series of Pro Series kits and such that we just throw those in there. And with that, that's actually a good transition in closing. I did want to highlight many of you guys called in today because you were invited by a distributor, and hopefully when you registered, you entered in the proper fields of the name of the distributor and the particular contact at your distributor who referred you to the presentation. That's really helpful both for us and for them to be able to know. But I'd also want to highlight that right now we're actually running a promotion on for the next month on our Smart Class Fiber products, and we've got a promotion running right now on our OLP82 and OLP87 kits that include the Smart Class Fiber device. It includes the probe microscope. It includes a hands-free carrier like the one that you see in this picture here. It includes the cleaning tools, everything that you need. It's included in those kits. And right now we're doing a special promotion where you receive an additional 10% off what you normally get. So that's running here for the next month. So I'd encourage you to, if you're interested in that, reach out to your distributor and ask them for more information on that. And if you are a distributor on the line here, get in contact with your JDSU sales rep and they can give you more information on that if you don't already know about that. And with that, we're actually 10 minutes over time right now. I'd love to keep talking. I could definitely talk for more, but I appreciate everybody calling in today and listening in. Be sure to check out our upcoming ones that are coming up in the subsequent months following this one. And with that, Karen, I'll turn it back to you.
Great, thank you so much, Tyler. Wonderful questions, and thank you everybody for attending. You will receive a follow-up email with recording information on meeting days, and as well as some additional information, so please look for that. And with that, I'd like to thank you once again for joining us, and this concludes our webinar today. Thank you and have a great day.